I found this very interesting oscillator circuit on the World Wide Web, radiohistory.com. I have forgotten the magazine, but I am sure that the magazine was of 1962. And in those days, of course, the transistors were almost always germanium transistors. That's why you read here the OC45 and also here the OC45. And we know from germanium transistors that they are more unstable compared to silicium transistors, and that is perhaps a reason why this circuit oscillated so easily. But when you have followed my channel, I'm more or less always busy with transferring these old circuits to the modern times, try to make them with silicium transistors, etc., etc. So, what are the important things to tell in that case? I used here a BC547 normal silicon transistor, and it is from China. And when you order BC547s in China, you will surely see that their current amplification is very high, in the order of 250 up to 300, while the old BC547s from Europe had an amplification factor in the order of, say, 150 or so. So that's something to take in account. Well, of course, we have here a negative voltage that serves the circuit. The positive is on ground, but of course we want now the negative on ground. So another transistor, negative on ground, no negative voltage here, but a positive voltage. And furthermore, there's not so much more to tell about this circuit, but they told that it could go to very high frequencies, and that's true in a certain way. When you want to change such a circuit to a modern circuit, you can use silicium transistors, silicium diodes here. So OR, that is a germanium diode, is also, I've used modern silicium diodes, and of course you can change the capacitor values here. I found out that this capacitor value, 500 picofarad, in the original schematic was, say, the time dependent capacitor. Of course the whole circuit is responsible for the frequency and thus the time dependency. So I changed a lot, and all these changes are here. To make it work, I made the value of this capacitor very high, in the order of 1 microfarad, and even then it worked on very high, not very high, but say 1 kilocycles up to 9 kilocycles or 33 kilocycles, even with this more or less high value capacitor of 1 microfarad. And also I bridged this capacitor with a 0.1 microfarad capacitor, that's 100 nanofarad. And also here, and I, of course, when you do all these experiments, you must be able to set the bias to each transistor differently, and that's done here by not using, say, the fixed value resistors that are, say, told here. In that case you will never get it working with another transistor or other type of transistor, or a silicium transistor or other type of germanium transistor. So use here a potentiometer to align the bias of this transistor and align the bias of this transistor. And this is the protective resistor, 1 kilo ohm always very important when it is not there and you turn here the wiper to say the positive lead. This must be positive here in the order of 4 volt. When you do that, the transistor will die immediately because of a too high base current, and that the same applies to that other transistor. That's the reason why you have here a protective resistor and also here. Schematic again. Let's go to the workbench where it is all realized in practice. So here it is on that workbench. The 47K potmeters, the protective resistors, oscillator, sine wave, etc., etc. And we can look on the scope and see the frequency that it generates. So even with this high, very high, 1 microfarad frequency dependent capacitor, and that's here. This is that high value capacitor, 1 microfarad. But of course you can change also the frequency by tuning the potentiometers. Some more light. So a very simple circuit, only for when you are interested in all these experiments, etc., etc. So let's put on the sound. You perhaps can hear the beep that this generator makes now at the moment. This is the waveform at the moment. Not a perfect sine wave, but anyway, it's on 7 kilohertz approximately. And well, in fact there's not so much more to tell. Let me change. Very important to tell is that it works in a limited voltage range. 4 volts. Here 3.9, that's 4 volts. Let me change the voltage here on the power supply and let's see what happens. Higher frequency, perhaps it's still audible, I don't know. The YouTube videos have a limited audio bandwidth, but anyway, 7.4 kilohertz, 8.3, 10 kilohertz, and here suddenly it stops. And now we are on 5.4 volts. So this is in a certain way a critical circuit, and when you want to operate it in a real circuit in practice, be sure that the voltage that you choose is okay. Now it's 3 volts, approximately 2.8 volts. Anyway, important to tell again, let's go to 4 volts, approximately. This is 3.4, but anyway, important to tell that when you turn the potentiometers here, of course the frequency will change, because all the components are in a certain way frequency dependent. And you can see when you want to say test such a circuit, the best idea is to lift up the value of the capacitors to get it working, and after that, when it works, you can say take them out, diminish their value, etc., etc. So that's the reason why you see here 0.1 microfarad and here 0.1 and also here 0.1. Final thing to tell is the 2 potentiometers that bias the circuit. Both are 47 kilo ohms. So I turn them now with my hand. Let's listen and see Now it's more or less inaudible, the sound, and it's surely inaudible now. 12 kilohertz, and I think, given the simplicity of the circuit, a quite good sine wave. And the original article, as far as I can remember, told that you could get to 200 kilocycles. Well, do your own experiments, that's all I can say. Again, 16 kilohertz, quite a good sine wave. 14, 10 kilohertz, and now we get in the audible range. And now when the bias is completely out of order, it stops. That's completely logical. There's another potentiometer here. That's this one. Here, this one. And I will change it now, and after that I don't tell more. Here you can also see that the waveform changes, the frequency changes. So all in all, you have, in my opinion, a quite good sine wave generator, especially for the higher frequencies, audio frequencies. That's what I mean, in the 7 kilohertz up to perhaps 50 kilohertz band. Of course, this is not perfectly pure, but anyway, when you set the bias, you get to a pure sine wave on 7.6 kilohertz. That could be useful. So, very simple circuit from the 1960s that works, though on low voltages in the order of 4 volts, 5 volts. But anyway, could be very useful. The schematic again, and thanks for watching.